This video was created by Macanas and Ekstrom, and it's going to serve as our Aero 320 final project video.
The focus of our project was on a reaction wheel. A reaction wheel is a flywheel that is mainly used for attitude control on a spacecraft or rocket body. It works by applying a torque to a flywheel, and in order to conserve angular momentum, an angular velocity is imposed on the system.
In our case, the dynamic system consists of the reaction wheel itself, the spacecraft that is controlling, and any other sensors contributing to the measurement or feedback to the reaction wheel. The figure to the right gives an example of a dynamic system for a reaction wheel or wheels. The equations of motion that govern our dynamic system are the rate of change of the Euler angles yaw, pitch, and roll, as well as the rate of change of the angular velocity, which is a function of the applied torque to the reaction wheel. So is our dynamic system continuous or discrete? Our dynamic system is discrete. Our differential equations of motion are defined in the continuous time domain. Modern day control systems are carried out on a digital processor that samples data coming in from sensors on a discrete basis. By sampling at a high frequency, the discrete system can approximate a continuous system. The figure to the right shows the approximation of a continuous system with a discrete system.
The inputs to our dynamic system are the state space equations derived from our equations of motion and the torque applied to the reaction wheel. These consist of the Euler rates, which can be replaced with the quaternion rates if need be, and the angular acceleration. The outputs to our dynamic system are the angular position and angular velocity. These will be changing based on the torque applied to the reaction wheel. The values will also be used to calculate an error from a set point to be redirected as input back to the system. The measurements our system would be taking are based on an accelerometer, which consists of Euler angles or quaternions and angular velocity. Another measurement could be position, in case our system would want to orient itself based on GPS.
So what's our feedback going to look like? The feedback for the control loop is going to exist in the form of an error calculation computed from a desired spacecraft orientation set point and the current orientation of the spacecraft. This error will then act as an input to the PID controller, which will be used to apply a desired torque to the reaction wheel in order to drive the spacecraft to the desired set point. Here's a block diagram representation of the control law that exists for our system. F sub s would be our input torque to our process in which our reaction wheel is contained. X sub s are our measurements from the system that we would gain from the accelerometer. These then get rerouted for an error calculation based on our set point u, and the PID controller calculates what torque we need to input into the system in order to achieve our desired orientation.
The performance metrics we will be using are attitude control and error, which will be the reaction wheel's ability to provide the correct orientation, as well as the PID controller's ability to minimize overshooting and or undershooting of this orientation.
Now we're going to talk about coordinate frames. Coordinate frames need to be established in order to relate all the data in the system to each other. The reaction wheel will have a coordinate frame of its own, as well as the body of the system, which in our case would be the spacecraft. And all of this will be referenced to an inertial frame, in this case, the Earth, as shown in the figure to the right. Here's a really cool video of a reaction wheel in action that demonstrates the dynamics of our system.